Hi, grade 6 students. It is day 18, lesson 9-5, page 389, numbers 7 through 29, the odds. If you recall, we talked about something called permutation a couple days ago. Today, we're going to talk about something called combination. But before we get started on that, please look at the examples on page 387 and 388, and then come back to this video, and we'll talk about a bunch of examples. Please pause the video now and go to those pages. Okay, welcome back. If you recall, permutation is a situation where we're trying to find the amount of outcomes when the order matters. Let's do an example of that. What if there were 5 people in a running race, and the 5 people knew that there was a prize for first place, $100, and a prize for second place, $50, and a prize for third place, $25. In how many different ways can those 5 people finish that race? And if you recall, we said that you could solve that problem by doing this math problem. And remember, in this case, the P does not stand for probability, it stands for permutation. And we read this, read it with me a couple times. The permutation of 5 people taken 3 at a time. Let's read it again. The permutation of 5 people taken 3 at a time. One more time. The permutation of 5 people taken 3 at a time. And we solve this by multiplying together, starting with the number 5 and going in descending order 3 times because of that second number. And in this particular case, we find that there's 60 different ways that you can arrange 5 people so that one person gets the first place prize, one person gets the second place prize, and one person gets the third place prize. 60 different ways of arranging those 5 students. So that's the idea of permutation, remember? Combination is similar but slightly different. Combination is when you're trying to find the amount of outcomes and the order does not matter. Permutation order matters. Combination order does not matter. Now, what do I mean by that? Let's imagine those 5 people were in a running race and 3 people were going to get the prize. But the prize is identical. If you finish first, you get a prize of $50. If you finish second, you get a prize of $50. If you finish third, the prize is $50. If you finish fourth, the prize is 0. And if you finish fifth, the prize is 0. Does it matter if you finish first, second, or third? No. As long as you're one of the top 3, you will get the prize. So nobody cares who wins first or second or third. They just want to be one of the 3 people that finish first, second, and third. Well, how do we figure out this situation of combination where the order doesn't matter? Well, it looks like this. The combination of 5 people taken 3 at a time. Say that with me. The combination of 5 people taken 3 at a time. And the way we solve it starts off similarly to a permutation problem. I'm going to write the permutation of 5 items taken 3 at a time, but I'm going to put that over the top of the second number, and we're going to use that number factorially. We're going to factorialize that second number. So it's going to be this problem divided by this problem. Now we already know what this problem is because we did it up here. We already know that the top of this equals 60. The question is, what's the bottom part of this problem? Well, 3 factorial, if you recall, means 3 times 2 times 1, which is 6. So our final answer in this case is that there's 10 different ways in which you can have 5 people in a race and they can finish such that 3 of them win the prize, and the prize is equal for all of them, so it really doesn't matter if they're in first, second, or third place. This is combination. So a combination problem where the order doesn't matter is basically a permutation problem over the top of the second number factorialized. It's a permutation problem over the top of the second number factorialized. Let's try this with 4 different example problems on the board. Stick with me on this. Let's start over here. Choosing 2 colors from 7 paint colors. You're going to paint your room at home, and so you go to Home Depot and you find 7 colors you like, but mom or dad says to you, you can only pick 2, so pick 2 colors and we'll use those to paint your room. Well, that's a combination problem. It doesn't matter which 2 colors you pick as long as you pick those 2 colors, and so combination problem. So we write the combination of 7 colors taken 2 at a time, and we think about that as a permutation problem of 7 colors taken 2 at a time over the top of that second number factorialized. This top part would be 7 times 6. The bottom part would be 2 times 1. We get 42 over 2, which is the answer of 21. So combination is a permutation problem over the top of the second number factorialized. Let's go to this next problem here. 10 people at a meeting are shaking hands with each person once. You're trying to figure out how many handshakes would occur in that situation. Imagine all 10 of those people are shaking hands with each other, and nobody wants to offend anybody by not shaking hands with other people. Before we get started on this, let's take a look at a simpler version of this. What if there's just 2 people in the room? How many handshakes would there be? There'd just be 1 handshake, right? With 2 people, there's 1 handshake. Can you see that up there? Nope, you can't. With 2 people, there's 1 handshake. What if there's 3 people in the room? How many handshakes would there be? With 3 people, there would be 1, 2, 3 handshakes, wouldn't there? What if there's 4 people in the room? How many handshakes would there be? With 4 people, this person, this person, this person, this person, this person, and this person. How many handshakes is that? That's 6 handshakes, isn't it? But it's starting to get complicated, isn't it? What if we add a 5th person to the room? How many handshakes were there? In addition to these, there would be this handshake, this handshake, this handshake, and this handshake. So how many was that? That was an additional 4 handshakes, so it jumps to 10. There is a pattern that's occurring here. I don't know if you notice it, but as we do this, the pattern is we added 2, then we added 3, then we added 4. So the next number would have to be adding 5. So if we had 6 people in the room, that would be an additional 5 handshakes. So that would be 15. But is there a way to do this using permutation or combination? And the answer to that is yes. Yes, there is. This is a case of the combination of 10 people taken 2 at a time, because you can only shake 1 person's hand at a time, 1 other person. So it's 10 people, and you're taking a look at 2 people shaking hands. Why is this a combination problem? Well, it doesn't matter if Frank shakes Bill's hand or Bill shakes Frank's hand. That's still a handshake. So the order in which Frank or Bill shakes the other person's hand doesn't matter. So again, how do we solve this? It starts off being a combination problem over the top of that second number factorialized. This would be 10 times 9, and this would be 2 times 1. We got what? 90 over 2. There'd be 45 different ways that those 10 people can shake hands if they shake everybody's hand that's in that room. Okay, let's move on to this one right here. Choosing 3 members of a track team out of a total of 8 members of the team to go to a particular meet. Well, what kind of combination problem is this? It doesn't matter if you're the first one picked, the second one picked, or the third one picked. As long as you're one of the 3 that's picked, you're going. That would be the combination of 8 track members taken 3 at a time, which becomes, again, a permutation problem over the top of the second number factorialized. So this would be 8 times 7 times 6 over 3 times 2 times 1. The bottom is 6. The top is, I don't know what that number is. 56 times 6 is 336. Now we got to do some simplifying of 336 divided by 6. That would be what? 6 goes into that 5, 6 times. That would be 56 ways. There's 56 ways you could choose 3 members of a track team from a track team that has 8 members to go to this particular meet. Finally, this last one, choosing 2 toppings for an ice cream sundae out of a list of 6 toppings. Well, that would be the combination of 6 items taken 2 at a time, which is really a permutation problem of 6 items taken 2 at a time over that second number factorialized. So that would be 6 times 5 over 2 times 1, or 30 over 2, or 15 different ways of choosing 2 toppings for an ice cream sundae from a list of 6 topping items. How are we doing so far? Let's do one of the problems on 389, shall we? One of the items on 389. Actually, we're going to do a couple of them. When you look at problems 5 and 6 on 389, can you tell the difference between whether or not a problem is a permutation problem or a combination problem? Look at number 5. It says, how many ways can 10 students finish first, second, or third at a science fair? Is that a situation where order matters, or is that a situation in which order does not matter? Order matters, doesn't it? You would rather be first place than second place at a science fair. So number 5 is a permutation problem. Okay, now that we know it's permutation, how would we solve problem 5? Well, that would be the permutation of 10 people entered into this science fair, taken 3 at a time because there's a first and a second and a third place. And the solving of this would be 10 times 9 times 8, or 720 ways. Look at problem 6. How many ways can you pick 2 puppies from a litter of 7 puppies? What do you think? Permutation, order matters, or combination, order does not matter? Hopefully you recognize order does not matter here. It doesn't matter if you're the first puppy pick or the second puppy picked. As long as you're picked, you're going to be one happy puppy. So this is a combination problem of 7 puppies picked 2 at a time. And we solve this by first thinking about it as a permutation problem over the top of that second number factorialized. So this becomes 7 times 6 over the top of 2 times 1, which is 42 over 2, which means there's 21 different ways to pick a puppy for this particular case. I hope this helps you. Please give me a call at 517-242-3138 if you're stuck. Thank you and have a good day.